Hello and welcome. I'm Alvin Richards, the product lead for Elasticsearch. I'm super excited to talk to you today about new search and query capabilities in Elasticsearch. We've been busy in Elastic creating new ways to search and find relevant data, including a new language. But before I begin, let me state there are already many ways to search for your data in Elasticsearch. So why do we need another? Well, let me take you through where we are today and the genesis for the evolution of search as we see it. Today, Elasticsearch is used by many different types of users. Originally, developers using Elasticsearch to add search capabilities into their applications through REST APIs. As the ELK stack grew, logs became a primary use case that brought a new group of users, SREs and DevOps teams. They wanted to use the power of search to understand and analyze the correlation in logs and then metrics and then APM data. As we added our security product, another group of users was added, the security analyst. They thought about the world in terms of events and threat detection. All during this time, we added many new ways to search and analyze data, Kibana and KQL, and then EQL and even SQL. Many QLs. That's a lot of ways to find the same thing. But there were still some challenges figuring out a schema design before you ingested data, joins and other sources of data, evaluating values during the query. So those are just a few gaps that made Elasticsearch much more exciting to use than it needed to be. So we took a long, hard look at what users wanted to achieve and the simplest way for them to reach that goal. The ESQL or Elasticsearch Query Language project was born out of this. Essentially, ESQL is three things. Firstly, it's a new query language that is designed to help incrementally explore data in a natural way. Rather than a big complex statement like a SQL statement can often be, it allows you to slowly add and refine and frankly debug the data results as you build up the search statement. Secondly, it's a new distributed compute engine. This provides a new way to scale out query performance, but also to add very new execution strategies. We'll talk a lot more about the compute engine later in this talk. Finally, we wanted to create a new unified query experience. Whether you want to specify a search, whether that's in Lens or Discover or creating an alert, ESQL will become a simple and uniform way to define that. So let's first take a dive into the language. Here's a very simple first query. You'll notice that we use pipes to combine stages of the query. Diving into the syntax a little, we first start with the index you want to search. In this case, it's the NYC taxi index. We can then compound multiple statements to further refine the results. Filters or predicates can be added with the where clause, in this example with a trip distance greater than 100. We can also compute new values at any point. Here we're creating the cost per mile by dividing two other values in the document. This new computed value is then used in another where clause to limit the cost per mile to be greater than 5. Finally, we can sort and limit the results. That's a very simple way to think through, supplement and augment the search step by step. Returning to the language components, there are 5 major groups. Projections, so that you can return just the fields you're interested in rather than the whole document. Filters to narrow down the documents of interest. And the ability to compute new values as well as aggregate sums, averages, and other statistical functions on the fly. All these computed values can be used in subsequent stages of the pipeline. Lookups and joins allow data to be combined from multiple indexes. This can avoid some of the schema denormalization tricks you may have had to do in the past. Finally, you can sort the data at any stage and limit the results. That's a pretty full and rich query experience. but let's show you this in action. So it's demo time. Here we are in Kibana. I've already selected the ESQL mode from the drop-down. We're going to use the NYC taxi data, and as you can already see, we have already projected a bunch of documents from this index. So we're seeing all of the fields of the documents, and that's a lot of data. So let's restrict that data by using the project clause. So we'll add the project, rerun the query, and we can now see just those two fields projected of the date, time, and the total amount. Cool, we've restricted the results. Let's now sort, but this data is unsorted, still difficult to see. So we're going to add in a sort, and we're going to sort by the total amount descending, and we'll see the total amount is $157. So that's super interesting. So you can see that you can easily build up step by step this search in an easy and simple way that you can inspect the results as you go along. So let's look at another query where we're going to build up a where clause to filter the data. So again, we'll do this from the NYC taxi data, and we're going to look for fares greater than $20, and so we get a bunch of results. I now want to restrict it to for rides where there was a cash payment made. So we're going to do it for payment type 1, which is cash, and now we can now start restricting those results further. What's really interesting to me is finding those generous riders who tipped more than $5. So again, we can add another where clause in where the tip amount is greater than 5, and we get a bunch of results. So still a lot of information here. And now that we've found our generous tippers, why don't we sort by that tip amount and find our top 5 tippers? So let's add those two clauses in. We're going to add in the sort by the tip amount, and we're going to limit to 5 just to give 5 results. So let's have a look. And if we look across here, we've clearly got an outlier here from this rider who, according to the data, tipped almost $4 million. That clearly is some erroneous type of data, which I probably want to now actually understand what's going on. So you can see it's really easy to build up these filters step by step, and you can see how you can sort and project data to really narrow down on the set of things that you are really interested in. One of the really neat things about the language is the ability to compute new values on the fly. So this allows you to transform your schema on read. So let's start a new query and let's compute the cost per mile. So here we have our new query, and we're going to compute the cost by mile, if I could say it correctly, by evaluating the total amount divided by the trip distance. So we can now execute that search, and as you can see on this last column here, we have the cost per mile. So that's computing that value for each document returned. Let's just sort of add a little further criteria. We want to do this just for trips that are greater than 100 miles. So we can restrict the results by adding in a where clause, super easy. Lots of information here, so let's just add in a projection just to hone this down to the things that we really care about, the payment time and the cost per mile. So great, we can see the payment type, cost per mile, and we can now see that there are some cost per miles that are just in cents. So let's sort of look at where the cost per mile is greater than $5, because that seems very erroneous or a very expensive type of trip. Clearly, we've got a whole bunch more than $5. And so let's actually sort by that cost per mile. And again, that's the computed value. This is not something that exists in the document. We're computing it. So we can add in the cost per mile descending, and we can see actually the highest cost per mile was somebody paid $39.67 per mile. Well, that's a pretty expensive trip. Again, what we can see here is we're building up step by step. We can examine, we can hone in on the exact things we're really interested in. There's one final search I want to show you. You can add aggregations into your search. It's really simple. So what we're going to do is we're going to compute the maximum number of passengers in each vehicle by the payment type, by credit card, cash, and so on and so forth. So here's our query, and it's super easy by saying stats and your expression you want to compute and what you want to group by in order to actually see your results. And so what we see here is the maximum number of passengers is 9 for these 4 payment types, and it's 5 for the 5th payment type. So rather than me visually counting this, because I'm pretty lazy, why don't we get ESQL just to compute the count of payment types for the maximums. So we're going to add in another clause where we're going to count the payment type. And we're going to do this by max passengers. And max passengers was this previously computed statistical function. So we can now run that query. And we can now see there are four payment types where max passengers is 9, and there's one payment type with max passengers of 5. So you can combine these aggregations in the same way that you can combine all the other sort of operators. And I hope that gives you a little flavor of how easy it is to discover, transform, and aggregate data with ESQL. I hope you now have a better feel of how simple ESQL is to use and some of what the experience in Kibana will look like. We believe ESQL will enable more types of users to be successful in finding the right data to solve their problem at hand, all done in a simple and intuitive way. So if that's the language, how does this all work underneath the covers? So let's spend a little time looking at the compute engine. There are 3 main goals for the compute engine. Firstly, it provides a new way to scale search independently from the data nodes and the infrastructure used to support the indexes. It allows for separate planning and execution of queries, utilizing the data nodes for retrieval. Finally, it has the ability to use different execution strategies to resolve the search. I'll show some benchmarks that will give early indicators for remarkable performance gains these strategies can have. Looking at the architecture, we have the coordinating function. Its role is to accept ESQL queries and parse it for correctness. Once parsed, an execution plan can be created and optimized. It's then passed to the runtime for execution. The execution phase then coordinates with the data nodes. The planner needs to figure out which nodes need to be coordinated with and passes down the request. The ESQL runtime then executes the search on the data node. This involves examining the relevant segment files in order to build the response. Ultimately, the results are stitched together by the coordinator before they are returned to the requesting client. So that's the simple part, but anybody who's built a distributed query processor knows there are many alternatives to finding the data. For example, do you broadcast to all nodes, or do you capture heuristics to target a subset? How does cardinality affect the search strategy? How much do you parallelize the search down at the data node? So there are many questions that affect execution strategy. So how do we go about solving this conundrum? Well, we've created a series of experimental strategies. Each has a different balance of the compute resources required to process the request. At the simplest, we have a thread per shard. This is similar to how aggregations are currently processed in Elasticsearch. Breaking this down, then you can add a thread per segment file. This means a lot more threads, but now the ability to process segments in parallel. But not all segments are the same size. So the document partition strategy allows multiple threads to process a single segment. Again, using more threads than CPU, but processing a segment can now happen in parallel. Finally, we can take a pool of available threads and apply that to the search, thus maximizing the compute that is available. So this is a lot of computer science fun, don't get me wrong, but what does that mean to you? Well, I'll show you some recent benchmarks. There is still a lot of work to be done and edge cases to be sorted out, but wow, I mean, some of the results are super interesting. Using the single thread per shard strategy, we already see some benefits. This is a simple query to find the average fare amount by rate code ID, for example, nighttime or airport rate. This gets a 1.4x improvement compared to the same query in Elasticsearch today. That's pretty neat. That's nice. If we take the same query and apply multiple threads to each segment, we get an order of magnitude improvement. So the same query now runs 14 times faster. That's very cool. Looking at a different query, this calculates the tip percentage for the fare and then calculates the overall average. In this benchmark, we're using a thread per segment, and we see a 16x improvement over today's Elasticsearch. Now, that's pretty awesome. But then the team went, I wonder if we could do better. So we take the same query and then we apply all the available threads in the pool to maximize the parallelization. And now we get a 33 times improvement. That's just jaw-dropping. And this is just early days. You know, we're still trying to look at ways of optimizing, dealing with many, many, many corner cases. And of course, your results are going to vary. But if I take a step back, my challenge to you is, what does ESQL bring you? All right, what can you now use Elasticsearch to search and find? What new application flows and insights can this query performance help you deliver? What flows can go from batch or long latency to now real time? Or what competitive advantages can this give your business? So I hope that gives you plenty to think about how ESQL will make your life simpler, but also can radically change the type of data and the volumes of data and the types of queries you want to execute. So that's where ESQL is today. Let me spend a few moments talking about what's next. In terms of the language, there are many exciting areas of development. We're adding support for date range and date manipulation. Dealing with histograms in a simpler way is super important for us to simplify. There is still work to simplify multi-value fields, that is, arrays, nested documents in reasonable ways. There is some complexity on how Lucene handles missing fields and null values, and so we want to smooth out that whole experience. Lookups are a critical new feature that we're adding, the ability to bring data from other indexes and sources into your result set. Inline conditions, if and case statements will allow greater flexibility to transform your data in line. And finally, we need to extend out the support for various data types in order to complete the whole picture. And there's still a ton of work on the compute engine. As you've seen, figuring out parallelization and utilizing all the compute available is critical. Some of that work involves delaying the load of documents as late as possible, but also including the data nodes required to process the search rather than broadcasting to everybody. Finally, to efficiently process query aggregations, we're adding more sophistication of how we plan and execute those operations. So there's still a lot left to do. Just to wrap up, what is the ESQL project all about? Well, it's a new piped language that allows a simple way to discover your data. It's easy to extend and refine reshaping of the data on the fly. Backing this new language is a new distributed compute engine. This allows new search strategies to be applied, allows search to be scaled independently. Finally, ESQL provides a unified search experience regardless of whether you're just visualizing your data, building rules or alerts, or just simply playing around with the data that you have. There's still a lot of work to be done, but we're very excited about the progress so far. Please follow our engineering blogs that have been published to keep up to date with the progress of the project. And we can't wait for you to get your hands on it and to take it out for a spin. Thank you so much for attending this session.